we can actually get a little bit more information about our linear approximations using what we already know about calculus. And we're going to use this idea of concavity here. If the graph of f is concave down near our x value, then we are going to overestimate in our approximation. So let's draw out a picture of a graph which is concave down. Perhaps it looks something like this. So this is my red function f of x. And if I were to say create the linear approximation right here, or just the tangent line right there, I'll notice that my linear approximation L of x, that blue tangent line, is above my function everywhere near that point of tangency. And that's not specific to just this x value right there. You could pick any x value that you wanted as long as the function is concave down near that x value. So if I had chosen, say, if I went with the classic horizontal tangent line, again, my tangent line is above my function everywhere near this particular x value. So I know I'm always going to be overestimating. Or even if I pick a point over here on the right-hand side, once again, I see that blue tangent line, that blue linear approximation is above my function. And what that means is that my approximation, so the point that I'm trying to approximate, which let's say is, this point right here, is higher than the same corresponding point on the function. So that'll at least give me some idea. I'll say, okay, I know that this linear approximation is close to my value, and I can tell actually, well, it's a little bit over the actual value because I know that the graph is concave down. Similarly then, if the graph of f is concave up near a, so if I draw a function which is concave up and I sketch in a linear approximation, our linear approximation will always be an underestimate this time around because this blue tangent line, this blue linear approximation, always falls below the value of the function at that same x value. So this point on my graph is lower than this point on my function because the graph is concave up. And no matter where I put that point, if I were to place it over here, or even having the horizontal tangent line, my blue linear approximation will always fall below the red function that I'm trying to estimate here, so long as that red function is concave up. So we can use this idea here in example 3. I want to find the linear approximation L to the function f of x equals x to the 1/3 power at x equals 27. So I say, okay, I want to start with I have the x value. Let's find the y value first. So I'll take 27 and plug that into my function. So this is 27 to the 1/3 power. Or perhaps it might be easier to think about that as the cubed root of 27, which is just equal to 3. So this is my y value. I still need to find the slope of my tangent line. So first I need the derivative, f prime of x, which is 1/3 times x to the negative 2/3 power, or 1 over 3 times x to the 2/3 power. And I want to plug in 27 here as well. So f prime of 27, this is 1 over 3 times, and I'm actually going to rewrite x to the 2/3. I'm going to rewrite that as the cubed root of 27 squared. So here, I'm going to take this kind of smaller steps here. 1 over 3, I know first of all that the cubed root of 27, that's just 3 squared. So I have 1 over 3 times 3 squared. 3 squared is 9 times 3, I have 27. So 1 over 27. This is my slope. So that is my slope of my linear approximation. And at this point, I have my x value, I have my y value, I have my slope. Let's write the equation of this tangent line. So y minus my y coordinate is 3 equals m. So let's see, this is 1 over 27 times x minus my x coordinate. My x coordinate here would be positive 27. So y minus 3 equals 1 over 27x minus 1. And then adding 3, I should have y equals 1 over 27x plus 2, or L of x equals 1 over 27x plus 2. Here is my linear approximation to my function f of x equals x to the 1/3 at x equals 27. So I have my linear approximation. My linear approximation is not all that interesting by itself. It's only interesting if I use it to estimate some values. So I'm going to estimate the cubed root of 26 here. So the cubed root of 26 is equal to, or rather not exactly equal to, it is approximately equal to 1 over, you can actually here, let's say this, it's approximately equal to L of 26, which is 1 over 27 times 26 plus 2. So this is 26 over 27 plus 2. Maybe I'll write this as 26 over 27 plus, what would that be? That would be 54 over 27. And adding these together, I have 80 over 27. This is L of 26, or in other words, this is approximately equal to the cubed root of 26. So you can get your graphing calculator out, and here I'm going to take 80 divided by 27. That gives me 2.9627. And if I take 26 raised to the 1/3 power, or the cubed root of 27, I end up with 2.9625. So I'm within 4 decimal places. I'm awfully close here. This is a great approximation here in this case. So this is my estimation. And I can actually do a little bit more with this now. It says, is this approximation an overestimation or an underestimation? Justify your answer. So I'm going to look at the concavity, which means I need to look at the second derivative. We said the first derivative, just so that we have it in front of us, was 1/3 x to the negative 2/3 power. So if I was to take or find the second derivative, I would have negative 2 over 9 times x to the negative 5/3 power, or negative 2 over 9 times x to the 5/3 power. So this is my second derivative, and I want to determine what is the concavity of my function near my linear approximation. Well, I based my linear approximation around x equals 27. So I'm going to take 27 and plug that into my second derivative. So f double prime of 27 is equal to negative 2 all over 9 times 27 to the 5/3 power. This is really, I'm going to skip ahead a little bit. Negative 2 over 9 times 3 to the 5th power. And this is going to be kind of an ugly number, so I don't really want to calculate it all that much. Really, it's the sign that I'm interested in. Numerator, that's negative 2. That's always going to be negative. 9 is positive. Times 3 to the 5th, that's going to be positive. I have a negative over a positive. It was going to give me a negative result. So what do we know? We know that the graph is concave down here. So this is concave down. If you need to make a quick sketch and see if I'm concave down, is this an overestimate or an underestimate? We may not know right off the top of our heads, but if we draw a function which is concave down and sketch in that linear approximation, we can say, hey, my tangent line is above my function. So I can tell that my approximation up here, this approximation of 80 over 27, this is an overestimate. And the reason for that is because f of x is concave down near x equals 27, and we were near x equals 27. We estimated at 26. So we can look at the concavity, determine whether our function is concave up or concave down, and then that will tell us, are we a little bit above the actual value or are we a little bit below the actual value?